Looks like we're a go.
Okay,
All right.
great.
All right. Well, welcome everybody to this new virtual BISH Bash. It's been a while. So today is going to be hosted by virtually hosted by DSP Concepts, and we're going to have a talk by Josh Morris, who's a engineer manager at DSP Concept and an old friend as well. But before we start, I just wanted to give a very, very quick introduction again of what BISH Bash is. So it's an informal networking meetup that's hosted by technology companies and institutions in the Bay for people who work or interested in audio. So we had like all these companies who and institution universities who hosted this meetup. So you see that DSP Concept actually hosted this meetup in the past, actually in person. That was many years ago before the pandemic. And yeah, like hopefully we'll have more people hosting this in the future. What's the point? So the point is to learn about the latest advances in audio, but not only signal processing, any audio related related fields as well. Share some of your knowledge, people who are the participant, but also the hosts with others, and make some connection, make some friends, have some fun, like some fruitful discussions and things like that. So I will ask the moment, I mean, if you can, like, we keep the momentum going, like spread the word. If you know someone would like to host the next meetup, or if you would like to host the next meetup, please let me know. You have all these links here. You can find all the links to the BISH Bash meetup. Just Google BISH Bash meetup. You can find the meetup website. There's also a YouTube channel with the previous presentation that we made. Just search for BISH Bash meetups. And we have also LinkedIn and Twitter. And just so you know, this is not the only BISH Bash. So we have, this one is the San Francisco BISH Bash, but we had like almost 30 meetups since 2013, 4 virtual ones since 2020, and like more than 1,000 members. But we also have a BISH Bash in Tokyo, in London, in Paris, in Latin America, and a recent one that just started in Italy. So you can just Google them and you'll find them, and they're doing well. And if you know other like places in the world, I would like to do this kind of informal networking meetup, please let me know. All right, that's it. And again, yeah, Josh, you can go
Sure.
ahead.
Yeah, I'll take over. Okay. Okay. So can you all see my screen?
Yeah.
Yep.
All right, cool. Okay. Thanks so far for inviting us to host this BISH Bash. We're excited to share about AudioWeaver. So today we're going to go through kind of a use case for machine learning with AudioWeaver. We're gonna look at keyword spotting, but maybe the bigger focus of the demo that we're going to do here is how AudioWeaver augments the machine learning lifecycle. So we'll kind of step through like a kind of hands-on demo, and we have a public-facing repo that we'll share out after this talk that you'll be able to go through and actually get to interact with all the kind of things I'm going to show you today. So before we jump into the demo, though, I'd like to talk to you a little bit about DSP Concepts and what it is we do, so that you kind of understand like where we sit, sort of in like the audio marketplace. We do quite a few things, and I like this graphic quite a lot because it shows kind of a lot of the things that we touch on. So our core product is AudioWeaver, which is kind of an orchestration and IP framework for embedded audio processing. And AudioWeaver kind of has a few different features to it. So we have our audio IP. We have prototyping hardware for sound bars and also for true wireless stereo earbuds. We have debugging tools. We have tuning tools. We have expertise. We're able to consult you on your projects. And we also have offices worldwide. So we're able to meet you where you are. So AudioWeaver is kind of has a few really powerful pieces to it, and it's kind of important that we kind of explain that so that you can kind of understand like everything that's going to be going on that we show you today. So the GUI that you're going to see is called AudioWeaver Designer, and that's the image that you're seeing here on the right here. This is how we orchestrate complex processing for embedded environments. It works in like a Windows OS, so you can design your whole system, and then you're able to take that system down to embedded targets. And part of Designer is also our optimized IP modules that we have, where we have low-level primitives to complete designs, like filters and various logic functions and stuff. And then we also have our own internal IP and third-party partners who offer a whole suite of solutions that you can use within your product that you're building. And then maybe one of the most powerful features of AudioWeaver is Awcore. And what Awcore is it's how we enable running on many different boards. So a big selling point of AudioWeaver is that you can be hardware agnostic, right? So it means that you can focus on prototyping and getting processing that is meaningful and be able to take that to a lot of different targets. So you're not tied to one particular hardware solution. And I think we all know supply chain, right? So this is a really important feature for kind of overcoming some of those sticking points. So this is kind of showing you how these things flow together, right? So we kind of typically start with AudioWeaver Designer, and that allows us to get our AWD layout, which is an AudioWeaver design. From there, we can generate an AWS script that will use server, which then takes your design and can run it on a board. And then we have Awcore that allows you to run everything standalone once you've finally finished all of your processing. So cool. That's kind of what AudioWeaver is, and now we'll kind of start to focus on the machine learning specific use case, right? So I think we're all kind of familiar maybe with machine learning and kind of the steps that we have to go through, right? Like we go and get a data set for our problem, right? Once we've decided what the problem is, we get that data set, we then inspect it, we maybe have to label some data, then we're going to prototype some features, try out a bunch of different models. Once we have a model that's performing with the metrics that we like, then we go and implement all of our hardware-specific code so that we can get it running on device, right? Like it's kind of a long, arduous process with a lot of pain points. And so what AudioWeaver tries to do is give you consistent feature extraction between your prototyping phase and your hardware phase, right? Because I think a lot of us are familiar with kind of Python workflow where we like use Librosa to kind of prototype our features, you know, or you maybe use some built-in modules from TensorFlow or PyTorch. And then when it came time to deploy, you have to figure out how to recreate those features in a more optimized language so that you can actually get real-time performance, right? And the solution that we're proposing with AudioWeaver is that you can use our already optimized modules for all these different targets using Awcore and be able to use the code that you've used in prototyping in production. So we're going to severely reduce the amount of time that you take to deploy to production or into the market, right? And so if we kind of like have this graphic here, which I really like, which kind of shows how we've taken this from like a 9-step process to a 6-step process. And a lot of this has to do with how we get models out the door, right? And I think like everyone's maybe seen a amazing machine learning project maybe die in the prototyping phase because like it's either too expensive or time consuming to move that model into production. And so what AudioWeaver does is kind of solve that pain point and allow you to move into production without having to, you know, internally resource a bunch more engineers to be able to get your model out to the public. So the benefits here for a machine learning development workflow, my personal 2 favorites, right, are the orchestration abilities. And I think we see the importance of this in ML in general. Like you see tools like Airflow becoming really important for building these complex ML pipelines that do some really complex processing in the cloud. And I like to think of AudioWeaver as being part of AudioWeaver being a kind of analog to that solution, where you're able to visually see how all your processing is orchestrated and works together, right? And that can be really useful for kind of explaining a system and maintaining a system when you have like many models running in production. And then, harping on this fact again, like it really simplifies that featureization process and reducing the time it takes to get on your target hardware. And you're also able then to, use inspectors to inspect your model performance on device in real time. And you're able to profile your model and your whole system block by block in Audio Weaver to see like where you're using memory, where is CPU getting used up and all of that. So you're able to really like move through your design and optimize like specific parts of your pipeline. So quickly, what are features? Features are a way of taking audio and describing it, right? We know for machine learning models, like it's good to have information that describes the kind of situation we've put our model in, right? And there are some models that use time domain signals, but we kind of know, like in the neural network case, that it helps to apply some transforms so that you can then use models to extract like structural information from the features you've created. And so Audio Weaver gives you a whole suite of options for getting that specific task done, right? So we have some analysis and synthesis blocks. We've got a short time Fourier transform, and we've also got weighted overlap add. And both these allow you to do things like ML noise reduction within the Audio Weaver ecosystem. And then for your kind of classifiers and other type of regression models, we have your other kind of popular features, right? You can either create power spectrograms, we have MEL spectrogram modules, we have an MFCC module, and we have an ERB module. And so you're able to use these kind of common features that you're used to working with your models within Audio Weaver and have that assurance that you've got an optimized implementation when you move into production. And in this demo, we'll be using TFLM. So we also wrap up some interpreters. Right now we have TFLM available in our product. We're also working to wrap TensorFlow Lite, and we're also working to get Onyx Runtime available, which should give you a path for both TensorFlow and PyTorch models when you're trying to run things on device. And TensorFlow Lite is kind of the most optimized interpreter for TensorFlow, and it's very focused on DSPs and microcontrollers and other embedded targets. And it's very useful for running on getting your models quickly onto device so that you can inspect how it's working in real time. You don't have to go through this lengthy model compilation process. You export your model to TF Lite, and then you're able to bring it into Audio Weaver and have it work with this interpreter. So in here is an example of us orchestrating a keyword spotting model, right? So you can see we have all our feature extraction going on this left-hand side. We have our TensorFlow Lite micro interpreter running, and then we rebuffer, and we're able to create line graphs here in Audio Weaver where we can see in real time the likelihoods that have been outputted by our model while listening to the audio in real time. And I think we've all maybe gone through the experience if you've tried to bring a model into production, how like you can be measuring metrics like in Python or in a notebook, but when you try to put it into like a real-time streaming situation, all of a sudden the performance or the way the model behaves is quite different. So for me, this is like huge where you can actually get to seeing what your model is doing, right? And getting that visual verification of like how your model is performing. And it also allows you to interact with it, which I think is huge. So, okay, so that's kind of what Audio Weaver brings to the ML lifecycle. We're going to move into a demo, but before I do that, are there any questions anyone has of what we covered so far?
I have plenty, but I'll wait till the end.
Okay. Is that Tom? Or maybe
Nope.
somebody else. Oh, okay. All right, so cool. All right, well, we'll jump into the keyword spotting demo then. All right. So we're going to jump into a notebook and I'll show that running. And we'll also show you kind of like the designs that we've created in Audio Weaver so that we can do feature extraction. And then we'll export a model in a quantized format and bring it into Audio Weaver and show the model running in real time and show visualizing the output of that model. So we'll run through Python package imports. We'll set up an initialized Audio Weaver. We'll import the mini speech commands dataset, which is a subset of the Google speech command dataset, which is much larger. We'll split that data set up. We'll read the audio files and their labels. We'll convert waveforms to spectrograms using AudioWeaver. We'll build and train the model and train it for 10 epochs. We'll evaluate the model performance, run inference on an audio file, save the model, and then bring it into AudioWeaver and run it. So cool. So switching over.
And we're getting some questions in chat. So,
Okay.
After the demo, maybe we can address some of those.
Okay, sounds
But
good.
I think that's a good place for questions.
Okay. Sounds perfect. Thanks, Adam. Yeah, I heard some messenger things. I can't see any, unfortunately, because I'm sharing my whole screen, I can't see what people are asking right now. Okay, cool. So I think a lot of people will be familiar with this format, but if you're not, what we're looking at here is a Jupyter Notebook, which is a nice little interactive environment for running Python code in the browser. The kind of wonderful thing about it is that you get the ability to use Markdown and also like visualize images and audio within the browser. So what I've done here now is I've just started executing the model and it's running. And you can see we're importing all of our dependencies. We're setting up a bunch of globals. Is that better? Can everybody stream my screen better?
Yeah, thanks.
All right, cool. Yeah, sorry. I roll pretty zoomed out, I guess. All right. Cool. All right. So we're allocating all of our globals and configuration parameters for AudioWeaver, and then we start an AudioWeaver instance, which is going to allow us to run AudioWeaver designs. So what we'll be doing is kind of constructing like our feature extraction pipeline in AudioWeaver. We'll export that to a binary, and then we'll use this with a Python Awcore, which is our Python package for interacting with compiled designs. And with that, we'll be able to featureize our data and train a model. So here we're just pulling our data down from Quilt, which is a data mesh for model storage and documentation. And then we split that data up, and then we just start building up our data loaders here. So the first thing we're going to do is read the audio and convert it to FRAC32, because that's what AudioWeaver expects as input. And we'll decode it, and then we'll load the labels. We build this function that'll load the waveform and the label. And it'll visualize it here. And as this comes up, I'll scroll back up, but I'll just do a quick overview first. So we'll convert the waveforms to spectrograms using AudioWeaver. And so here what we're doing is loading our AudioWeaver binary, like I said, and then using this function here to load audio samples a block at a time, because AudioWeaver is block-based processing, and put it through our feature extraction pipeline. We will get a spectra at a time, or each time step. We'll bring that back into Python and accrue it, and then we'll concatenate that all together to create a TensorFlow tensor that we can use with TensorFlow. So just scrolling back up, because I see we're catching up. Here you can see we've loaded the audio and we're visualizing it. And then here is a picture of our feature extraction pipeline. So you can see here how we've used these AudioWeaver modules to build up this complex processing very quickly, right? And you can see how this is all routed together. And we're using the spec sync here as our way of getting that complex magnitude out and back to Python. So cool. And then here we're just showing we're loading the audio. And then what we've done is verified our spectral features. So you can see here's the waveform, and here's the spectral features we created with AudioWeaver. You can tell things are aligning, so we're feeling pretty good about how things are looking. So we keep on rolling down. You can see we've loaded up some more audio files. What you're seeing here is some DC offsets within the data set. But you can see the files that don't have DC offset issues are loading just fine. And you can see how these words all compare. And so now that we've convinced ourselves that our data loading is working and our processing is working with AudioWeaver, we can move into training our data set. So we're just going to build our train data set, validation data set, and test data set, set up like our model, right? Define all our layers. And then we're going to compile our model with our optimizer and our loss, and specify that we're interested in tracking accuracy. And then we'll kick off this model.fit, right? And this is going to run for 10 epochs. So while that's running, we'll see our accuracy increase over time, right? And we'll visualize our losses over time for both train and validation, and we'll see that those are both converging nicely. And so once that finishes, we'll export the model to save model format in TensorFlow. And then we'll store that model, and then we're going to evaluate the performance against our test set. And then we'll display a confusion matrix. We'll run some inference on some test files to verify that we believe the model is working. And then we're going to go ahead and export the model to TF-Lite format. So here we're both going to export to floating point, and we're also going to do a quantization so that of int8 of the model. And the model that we'll use within the design is the int8 quantization. So as this finishes executing, we'll bring it back into AudioWeaver. And the nice thing is I've already kind of run this notebook ahead of time, so I already have the model. So we can go ahead and step into AudioWeaver and start looking at how that functions. So you can see here, this is the image that I showed earlier of feature generation. So this is the design that we've used to create our features. And then here's our design for running inference. So you can see it's the same processing pipeline here, but then we're adding a buffer up so that we can concatenate enough spectral time steps that satisfy the model that we've trained. We'll then take that model. We're going to take, it returns an 8-sample wire, but each of those samples represents a class. So we're going to use the set wire properties to split our 8 samples into 8 wires. We're then going to do this rebuffer, which accrues samples in like a circular buffer fashion. So this -4 here just says that we're going to keep 4 time steps, and it's a first in, first out queue. And so that'll just be visualized here in this sync. So if I go ahead and run this design real quick, I've recorded a audio file of me just saying the keywords, and it's now running through this design, and we can actually come here and take a look at the model output over time. So you can see we've named all our wires coming in to this sync, and so we can actually see all the individual class outputs here in real time as the audio is being fed through the design. So this is nice, right? Because we can kind of see how the model is behaving. And if you were doing some sort of downstream processing based on this, you're able to, kind of choose like pinpointed locations within your design to verify if things are working, right? So it makes troubleshooting much faster and interactive. And then the other thing that I really like, and we were talking about this, is we can do a profile of block by block of AudioWeaver so that we can see where all of our processing is being used, right? And so we can actually see, the percent of CPU that we're using, what block it is, how many megahertz, and then you can also see the memory consumption that's taking place, right? And you can actually see the different heaps as well. So this is really nice because we can actually like view our system and troubleshoot and inspect it pretty quickly. So cool. And unfortunately, I'm traveling right now, so I don't have a board with me to run this on. But what you would do if you did have a board to get this running, you can come here in AudioWeaver and you just change this connection to USB. And then if you had a board connected, you choose from this drop-down menu the board that you're interested in running. You click change here, and then when you click run up here on this design, it'll actually go and run the design on your board. And then you can still use these same sync modules and profiling that we've looked at to inspect model performance. But now you're looking at the device that you're looking to go into production with. So it's a very kind of powerful system, right? And so we'll just go back to the notebook here real quick and just verify all the model performance. So you can see everything's finished training. So you can see we ran for fully 10 epochs. We ended with about a 90% accuracy on the train set, and then 86 on the val set. And then if we visualize our loss over time, we can see things are kind of converging nicely, how we like to see. And then we can create our confusion matrix here, which is always cool because you can kind of see which words are getting confused with others, right? So you've got like no and go, right? Which kind of makes sense. And then like no and down also get confused. So kind of your more similar sounding words are getting confused, right? And then here's our prediction for a file that has no in it, and you can see most of the likelihood has been assigned to the no class. So we're happy with how this model is performing. So cool. All right. So to go back to the slides real quick. That concludes the demo, but as a thank you for coming to attend this BISH Bash and watching our demo and learning about AudioWeaver, we'd like to give you a 90-day extended trial for AudioWeaver Pro. You're able to usually get a 30-day trial through our website, so this is giving you, 3 times as long of a trial. So if you use this code here, go to this URL and use this code, you'll be able to get that extended license so that you can spend some time messing around with AudioWeaver yourself. So cool. That concludes my presentation, so I guess we can move into answering some questions now. So let me get my screen to where I can see everybody again. So should we start maybe with the ones that have come in through the chat?
There's no clapping button in Google Meet.
No
What's that?
clapping button.
No cloud. Yeah.
No, great
Thank
job,
you.
Josh. That was really
Thank you.
great.
Cool.
Thank you, Josh.
Yeah, thanks. I know I went really fast. If anyone's interested in doing like a longer sit down for this, like feel free to reach out and we can schedule a longer call with you and your company where we can step through this stuff more thoroughly. Okay, looks like Lee's asked a few questions. Are the feature extraction modules open source? How do I diagnose problems or produce variants of an implemented module? Lee, the modules aren't open source, but we do provide very low-level implementations of basic DSP. So if you really want to have that level of control, what you could do is build your feature extraction from those low-level modules, and then you're able to use all of our inspectors to visualize the output of all of that processing. You can also file issues with us if you find something wrong with one of our modules. But I would encourage you, if you want to have that level of control, to go ahead and use those low-level DSP modules. Though we do provide higher-level modules too to help you get to getting something faster. Are all the audio processing on DSP hardware expected to be floating point? No, actually. We do provide modules that are FRAC32. We do like float. I like our CTO saying life's too short to do anything but float. Or I think his quote was life's too short for FRAC32. But float just makes things nicer. But we do have modules for if you need those more optimized types. And then will you release a Linux version of AudioWeaver Designer? I think there's some discussions going on internally, but there's nothing planned. Like there's no dates assigned to anything, but it is something I think we would like to do, but it's definitely some future work. Now, what you can do, and this is what we're doing internally, is that you can build your AudioWeaver binaries for Linux. And then we also have AWcore, which can be built for Linux. And so you can actually use the Python AWcore wrapper in a Linux environment. So the demo that we're running here, actually, that's exactly what I did. I designed the feature extraction in AudioWeaver and then exported the binaries. And then we're using a Linux implementation of Python AWcore within a Docker container to run the feature extraction pipelines. So we didn't really look at the repo. And maybe I should pull that up and take a look. But we have tried to use modern tooling as well so that you can use code snippets from this demo to help get it into your company's production pipelines quickly. So hopefully that's scratches your Linux itch. I'm a big fan too. So, and I think, okay, looks like we got another question here. Does AudioWeaver support models from tools other than TensorFlow such as PyTorch? And how about Onyx? Yeah, okay. We have an Onyx module that we're working with internally that we're working to get a release date on. Now you can export models from PyTorch to Onyx. And so that would be the solution for PyTorch right now. We have talked with PyTorch about like their TensorFlow Lite, TensorFlow Lite Micro type solution, but they're still kind of in a planning phase from what we can tell. I think they're planning to make some announcements kind of, late this year or early next year. And then we'll hopefully be able to bring that work into AudioWeaver. Your other option, if you really want to use PyTorch, we also offer the ability to create custom modules. So if you wanted to go the route of compiling a model and bringing it into AudioWeaver, that's also a valid solution. So we do have some flexibility there. If you've got your mindset on a specific framework. And then Ohad, hopefully I said your name right. Looks like you've got your hand raised.
Yeah. I was trying to be polite. Doesn't always work out. Got a lot of questions, but
Let's go.
First of all, what kind of hardware do you support? I mean, I'm assuming you have some kind of compiler effectively that takes your int8 model and makes it amenable to be flashed upon a certain. I'm not a hardware dude. Yeah.
Okay.
As you can tell.
Yeah, no worries. So you're looking specifically to like the model or like the entire feature extraction pipeline, or both?
Can you do both? Or,
Yeah.
So you have some primitives for several distinct types of hardware, but which ones are they? And more importantly, how hard is it to add more?
Right, that's a great question. So Awcore is where we get that flexibility of going to different targets, and that's kind of handled through AudioWeaver. We work with a variety of boards, like the ST 747 Disco board is a board that we support. And now I'm blanking on all the boards we support because this is the kind of thing that happens when you get asked these questions.
Mm-hmm.
But we've got support for ARM hardware too. We've got Hi-Fi support as well. Now what's supported by TensorFlow Lite Micro is different from AudioWeaver because TensorFlow Lite Micro is taken from open source, and we brought that module into AudioWeaver. So as far as your models are concerned, you'll need to check the repo. Now there is quite a lot of support there, and a lot of the companies that are building these boards are directly contributing to TFLM, and so we are seeing optimized implementations appear there.
Mm-hmm. Okay. And you were showing this nice live demo that you're listening and you're seeing the nice graphs and you're getting an immediate understanding of how your network is responding to certain keywords. But do you have any? First of all, is this something that happens post quantization, or is this the models as they are in software? I mean, do you have an emulation of the hardware and how the hardware would react?
Yeah, so ideally, because I'm traveling, I don't have a board with me, but I'd have a board connected here. And what I showed there quickly, and maybe I went too fast, is like from AudioWeaver's server, which is kind of that smaller window that had all that text in it with like a play bar and stuff. In there's a target option, and when you choose target from that drop-down menu, you're actually able to go in there and look at a bunch of different connections on your computer and actually select the connected hardware. So if you have the board connected to your computer, you can actually it's not even an emulation. You can actually run the actual hardware. You have it sitting on your desk.
Oh, so you're reading the responses from the hardware.
Exactly. So what you're seeing is those syncs are displaying information that's coming back from those boards.
Mm-hmm. And last one, do you have any posterior processing evaluation?
Can you clarify that a little bit more for me?
Where you're looking at the activations and then applying additional processing on the activations.
Right. Yeah. Yes. Okay. Great question. Yeah. So, tuning the classifier to that extent's a little bit out of the scope of this particular demo, but we have this block called hysteresis, which allows you to set a threshold and like another threshold for which like the classifier lets go. So, you can do your favorite like ROC curves within Python and then actually go into AudioWeaver and set those values within the hysteresis module. We also have a bunch of statistics modules. So if you wanted to do something like, median filtering or mean smoothing, those are all valid operations that are available to you in AudioWeaver as well.
And they can be applied in the hardware emulation, or while you're listening to responses from the hardware.
Yeah, exactly. Yeah, and you can actually tune them while you can actually turn knobs live on device. And I think that's pretty powerful, right? Because like I think we're all kind of familiar with like you set all the values, then you had to flash the board, then you run the board, you find out you set it up all wrong, it's not functioning the way you want it to, and you're like, okay, great, now I got to try a new set of values, put that on the board, spin it up again with my test file, and like, oh no, it's still not working, right? So like with AudioWeave, you can actually get in and turn the dials and see how things are playing out, right? So it's nice because you've got that tuning interface that's speaking directly to the device when it's connected to your computer.
Thank you very much.
Oh, great questions. Thank you for asking. So cool. Any other questions anyone has? These have been fantastic questions. I'm happy to answer any more questions that people might have. Cool. So what we'll do is we'll share out the slides from this, and we'll also share a link to this repo so that you're able to pull this down and start interacting with this stuff. And like I said, feel free to reach out with questions. We'll include emails so you can reach out. And if you want to do a longer sit down about this demo and what AudioWeaver can do for you or your company, we're happy to meet with you and discuss further the possibilities of collaborating together.
And if you want to take advantage of the Pro Edition trial, I dropped that information into the chat.
Fantastic. Thank you, Adam. So cool. All right. Well, that ends like the presentation phase. So I think we can probably stop recording and then.
Thanks, Josh, again.
Yeah,
Excellent
thanks for
job,
having me.
Josh.